Hello everyone. In this part of the course, we are going to start designing the controllers in the state space domain. But before going deep into the topic, we will have a brief introduction to the state space representation of the systems. In this video, we will see how different representation forms of the systems in the state space domain could be indeed obtained. So first of all, you should know from the previous course that the state space model is a representation of the dynamics of an nth order system, which could have multiple inputs and multiple outputs, as a first order equation in an n vector, which is called the state. So we have a system with n number of indeed differential equations, and then we can convert it into a single equation in the form of n vector, and that vector is called the state vector. So we need to convert nth order differential equation, which governs the dynamics of the system, into n first order differential equations, and then we put it in the vector form to obtain a single equation. The state of the system is represented by a set of variables, and those variables are called the state variables. So we will deal with the state variables, and they will give us complete information regarding the behavior of the system. They allow us to know the future state, so how the state of the system will be in the future. Once we have the present state, or the initial conditions, the excitation inputs, and the equations which describe the dynamics of the system. So having these three, we can predict the future states. We can obtain the value for the future states. Here you can see a simple block diagram of the dynamic system state x of t, which receives, if we provide indeed the input, the initial conditions, and the equations governing the system, we will be able to obtain the outputs of the system and also the next state values. Well, again, before going into the details of state representation of the systems and also the controller design in this domain, we already have covered the classical techniques or the frequency domain techniques for designing and analysis of the system and designing of the controller. And those two were the root locus and the body response analysis and synthesis. The controller design for the system using the state space approach is called a modern technique or time domain technique. And we will see how to use this. This will be indeed another approach for designing the controller. Here we see the general state space representation for a system, for a given system. X dot equal to ax plus bu is the state equation, and y equal to cx plus du is the output equation. Over here, x is the state vector or the state variable. X will be in the form of a vector of x1, x2, x3 down to xn. X dot is the time derivative of the state vector. So it's you derive x with respect to time in order to obtain x dot. Or we can say that x dot is equal to dx over dt. And we are in the time domain. So we can say x dot of t. Y is the output vector. So it could be a single variable or it could be a set of the variables. U is the input or control variable. U here is the input variable or control variable. And again, it could be in the form of a vector. So you can see that with the state space representation, we can deal with the multi-input, multi-output systems. So those are the variables. that we deal with. And then we have a given number of matrices and vectors. A is the system matrix. It's an n by n matrix, where n is the order of the system or the number of the states. B is called the input matrix. Its size will depend on the number of the states, so it will be n by n rows by m, where m would be the number of the inputs. If m is equal to 1, then it will be in the form of a vector. C is called the output matrix, and D is called the feed-forward matrix because it shows the direct pass between the input and the output, so it's called the feed-forward matrix. They might be in the form of a complete matrix or a vector depending on the number of the input and outputs. Once we have the transfer function for a system provided, we can derive the state space model out of that. So basically here the aim for us would be to start from the transfer function and obtain the state space model for the system. Sometimes the state space model could be indeed derived directly, referring to the equations which are governing the dynamics of the system, or sometimes that we have already the transfer function representation for the system, we can obtain the state space representation as well. One thing that you need to keep in mind is that the process of converting transfer function to the state space model is not unique. So we can have a single system which is represented by different state space models. So there are various realizations possible, but all these realizations are equivalent in terms of the properties of the system. However, one representation might be better when we want to perform a particular task. For example, when we want to design a controller, or when we want to design an observer, as we will see later, or when we want to analyze the behavior of the system. So depending on the situation, we might prefer one of the representations, but you keep in mind that they are indeed equivalent to each other because they all are representing the same system. There are different again, ways to represent the systems in the steady state domain. Here we have 3 of them that we will cover in this course. There's the controllable canonical form, or CCF, the observable canonical form, or OCF, and the Jordan canonical form, JCF, that we will cover in this lecture. I'll go through the details of each one of them, how to convert the transfer function into any of these representations in the next videos. I think that's all for this video. Thank you for watching, and see you in the next video soon.